Dear student, myself Dr. SUREKHA Jaiswal, Head Department of Physics, Moreshwar College, Bhokardan, District, Jalna. Today we will see Electrodynamics, paper code number 302, paper number 16, semester 5. Now, application of Gauss law. First application, symmetric charge distribution. Contents are: first, electric field due to a uniform charge sphere. Second point, electric field for a point on the surface of sphere. And third is electric field for a point inside the sphere. Now, second application, electric field due to charge cylinder. And also we learn here Gaussian pillbox and Poisson's equation and Laplace equation. Now, application of Gauss law. First point, symmetric charge distribution. Electric field due to a uniform charge sphere. Now, in case first, calculate the electric field outside a uniform charge solid sphere of radius r. See in figure, that's uniform solid sphere having radius r from the center O. Now, let the total charge Q be distributed uniformly over a sphere of radius r, and let P be a point at distance r. See that point having the distance r from the center O of the sphere. Now, let us draw a spherical surface called the Gaussian surface of radius r. Now, that spherical surface that is having dotted, that is a Gaussian surface having radius r from the center O as shown in figure. Now, due to the spherical symmetry, the field is to the surface and has the same value at all points on the surface. For small surface dA, the electric flux is through entire Gaussian surface is given by phi equal to closed integral of E into dA, and therefore phi equal to E into closed integral of dA. Therefore phi E equal to E into 4 pi r square, where the integral of closed surface dA equal to 4 pi r square, that is the surface area of the Gaussian surface. Now, Gauss law states that closed integral of surface over surface S E into dA equal to Q enclosed upon epsilon 0, where Q enclosed equal to Q. Therefore, closed integral over surface S E into dA equal to Q upon epsilon 0. Now, putting the value of Q equal to 4 by 3 pi r cube into rho, we get closed integral of over surface S E into dA equal to 4 by 3 r cube into rho upon epsilon 0. Now, E into closed integral over surface S dA equal to 4 by 3 pi r cube rho upon epsilon 0, and since closed integral dA equal to 4 pi r cube, therefore E into 4 pi r square equal to 4 by 3 pi r cube into rho upon epsilon 0. Therefore, E equal to r cube rho upon 3 epsilon 0 r square. Now, in case second, electric field for a point on the surface of sphere. Now, so E into closed integral dA equal to Q upon epsilon 0. If a point lies on surface of sphere, then closed integral dA equal to 4 pi r square, and therefore E into 4 pi r square equal to Q upon epsilon 0, and So E into 4 pi r square equal to Q upon epsilon 0. Therefore E equal to Q upon 4 pi r square into epsilon 0. Now in case 3, electric field for a point inside the sphere. See in figure. In the case, construct a Gaussian surface of radius r inside the sphere as shown in figure. That dotted circle is a Gaussian surface having the radius r. Charge enclosed in the Gaussian surface is Q. Now for a small surface area dA, according to Gauss law, closed integral over surface area E into dA equal to Q dash upon epsilon 0. Therefore E into closed integral over surface area dA equal to Q dash upon epsilon 0, and as closed integral of dA equal to 4 pi r square, that is the surface area of Gaussian sphere, and therefore E into 4 pi r square equal to Q dash upon epsilon 0, and therefore E equal to Q dash upon 4 pi r square into epsilon 0. The charge density rho equal to Q dash upon 4 by 3 pi r cube, and therefore Q dash equal to 4 by 3 rho pi r cube, and therefore E equal to 4 by 3 rho pi r cube and upon 4 pi r square epsilon 0, and therefore E equal to rho r upon 3 epsilon 0, and this is expression for electric field intensity due to uniformly charged sphere at a point inside the sphere. Now electric field due to a charged cylinder. Let us consider an infinite cylinder of radius r. See in figure, this cylinder having the radius r. As cylinder has the symmetrical nature, the electric field will be perpendicular to the axis of the cylinder and will be directed away from it, and the field E has the same magnitude at the same distance from the axis. Now to determine the field at a point P as shown in figure C, that point P having the distance r from the axis, consider a cylindrical Gaussian surface of radius r and coaxial with the charged cylinder as shown in figure C, and the two end surface of the cylinder are perpendicular to the axis. Therefore the field being tangent to the surface will be 0, and the electric flux through the cylindrical surface is given by 2 pi r into L into E, where L is the length of Gaussian surface as shown in figure. That small L is the length of Gaussian surface. Now in case first, if r is greater than r, then the charge enclosed by the surface is lambda L, and therefore according to Gauss law 2 pi r L into E equal to lambda L upon epsilon 0, and therefore E equal to lambda L upon 2 pi r L into epsilon 0. In case second, if r is less than r, then in this case the charge enclosed by the Gaussian surface is r square upon r into lambda L, and as if L is length of the charge is lambda L equal to 4 pi r square lambda into rho, where rho is lambda upon pi r square, and so now the charge obtained by the Gaussian cylinder is pi r square L into rho equal to r square upon r square lambda L, and therefore pi r square rho equal to L into lambda into r square upon r square. By Gauss law 2 pi r L into E equal to L lambda r square upon r square, and therefore E equal to r lambda upon 2 pi r square into epsilon. Now next is Gaussian pillbox. To determine the electric field to a finite plane, this carries uniform surface charge sigma Bewley Gaussian pillbox extending equal distance above and below the plane as shown in figure. Now applying Gauss law to the surface, closed integral E into dA equal to Q enclosed upon epsilon 0, and therefore total area is 2A due to the top and bottom surface of the pillbox, that is a Gaussian pillbox, and therefore closed integral E into dA equal to 2A into E, and the side pillbox do not contribute anything to the intensity, so 2A into E equal to sigma A upon epsilon 0, where sigma is the surface charge density. Therefore E equal to sigma upon 2 epsilon 0 into n cap, where n is a unit vector to the surface, and this equation is giving electric field due to an infinite plane which carries charge sigma. Now Poisson's equation and Laplace equation. Now scientist Poisson's derive this relation del square V equal to minus rho upon epsilon 0, that is related to electric potential and charge density. Now electric field is the gradient of scalar potential E equal to minus del V. The fundamental equation of E equal to, that is del dot E equal to rho upon epsilon 0, and also we know del cross E equal to 0. Now putting this equation 1.19 in equation 1.20, see here we get del dot E equal to del dot minus del V, that is del dot E equal to minus del square V, and therefore del dot E equal to minus del square V. Apart from the repeating minus sign, the divergence of E is the Laplacian of V, and thus the Gauss law can be written as del square V equal to minus rho upon epsilon 0. This is known as Poisson's equation. If in the area where there is no charge, so that if you put rho equal to 0, then equation becomes del square V equal to 0, and this known as Laplace equation. If we take curl of E, then we get del cross E equal to del cross minus del V, and therefore del cross E equal to 0. Then here we use the curl law to give an idea about E, that is del cross E equal to 0 permits E equal to minus del into V. Thank you.